Hello and welcome. I'm Corey Kell, creator of FlatEarthIntel.com, and this is a redo of part 2, putting it all together, video 11.1. I found there was an inaccurate slide, so I had to change out. I think I added 1 or 2 more slides to the original presentation as well. So with that, we're going to continue on with the part 2 of the 2-part presentation, putting it all together using the sun. What is the fundamental flaw in the globe model? Basically, it's the sun at 90 degrees. That creates a huge problem for the globe model. I know some people don't believe that the 90-degree angle exists for the sun, but it exists in both models. And that's defined by the Tropic of Cancer, the equator, and the Tropic of Capricorn on both the globe and the flat Earth model. So that delineates the sun. That's the sun's operating range for both models. The difference in the models is that on the globe model here, in this diagram, it tilts to keep that sun at 90 degrees. You can see here up at the Tropic of Cancer in the north, it tilts for the summer sun in the summer sun season. And the only time it's at 90 degrees for both hemispheres, the northern and southern hemispheres at the equator or during the equinox. And then as it tilts back the other way, for the Tropic of Capricorn, 23.45 degrees at that tilt, as that globe model is in the ecliptic. Again, for the flat Earth model, that sun is just orbits over the top of the flat Earth model at 90 degrees. So that lollipop, it's like a lollipop here on the left. The only difference is the lollipop, instead of being upright on the flat Earth model, it's to the side on the globe model. Very simple application. The surveyed triangle. And the reason that once you get an object to 90 degrees, that becomes a huge problem. It's kind of like a flag on a flagpole saying, well, that flag is in a certain distance because it's hanging up there on a 90-degree flagpole. And it's like, yeah, that's not going to work too well because you can use a line of survey or the line of measure, the hypotenuse, or measure the vertical angle on that hypotenuse. And then that becomes part of that surveyed triangle, whether you have 1 or 2 observers or 2 observers in a simul. And we can identify the sun's position by doing a sun plot, especially during like the equinox when it's at the equator, sun's at the equator, or during the summer solstice up in the northern hemisphere when it's at the Tropic of Cancer. We know that sun's exact position. And again, that becomes a huge problem for the heliocentric model. Why? Because it's in that triangle measure, that surveyed triangle. And then that becomes then we can tell that the sun is between 3,000 and 4,000 miles, not 91 to 94 million miles. Again, big problem for the heliocentric globe model. And again, the line of measure, simply it's within our visual perspective, is example 1. If it's outside our visual perspective beyond it, then we wouldn't be able to see that object. We wouldn't be able to obtain a vertical angle measurement. It's what we physically see. Very simple process, very simple application. Vertical angle is the measured angle to a height to an object. That's the simple definition of it. When we're doing testing such as the 45-degree sector test, we have to know that that limit and measuring the vertical angle, especially for the globe model and the flat Earth model. Measuring vertical angle of the sun, we need to know the sun size in the heliocentric model is 965,000 miles and some change. Half sun is about 482,000 miles. When we sight in on it, when we're testing it from the globe model, we always go center mass of that object, and then all we're doing is we're getting that spread, that difference, and that's the limit, the outer edge of it. And have to remember that when we're on the globe model, we're at the observer is at an angle to that sun at the time of measurement. So if we're doing the 45-degree sector test, our surface angle or observer angle is over here is at 45 degrees. And if in this example, if we have a 50.1 degree vertical angle measurement to the center mass of the sun, all we're simply doing is adding these two numbers together. We have to include that surface angle and the vertical angle. Adding them, we get a 95.1 or 5.1 over the limit of 90 degrees. Why? Because the sun is always 90 degrees in the tropics. Yeah, that's a huge problem. Knowing that limit is very important. And this is how we can test that heliocentric model to see if it's actually correct. So then what we do is we go to calculator.net, go into the right triangle calculator. And before we do any calculation, we want to make sure all these fields are empty, they're blank. We're going to put in 2 pieces of information that we've obtained. we're going to put in an angle A up here. We're going to put 5.1. That's the overage, or the degrees over the limit. Remember, we had a total of 95.1. The observer angle or surface angle, and the vertical angle is 95.1. That's 5.1 over the limit. We put that right here in angle A. In B, we're going to put the sun's distance in the heliocentric model at the time of observation. Then all we're going to do is we're going to press calculate. Very simple. All we're doing is adding two data information inputs and hit calculate. Once we do that, this display is going to come up in the right triangle. It's going to give us the answer, or the spread, in A. A is going to be the answer to our spread, and the answer is 8,429,000 miles and some change. The sun, if this number exceeds the heliocentric sun size, we've exceeded the heliocentric model's limit by a lot. Remember, the heliocentric model sun is only 965,000 miles, and we're actually only measuring half sun, which would be about 482,000. So we're way over the heliocentric model's limit. And again, that is the spread. That sun would have to fit in there. That spread would have to be much smaller. We'd have to be right at that limit. So we're way over the limit. Remember, our two input data given is B at 94 million miles and some change, and then our angle is 5.1 over the limit. So again, this gives us the spread. This tells us that the heliocentric globe model does not work. The math is bad. And again, that's why the heliocentrists avoid vertical angle, because they know it doesn't work. It is way off. And again, we give our givens B and the 4.1 over on our vertical angle measurement. And if this sun, again, if this greater size, greater than the sun, and it is by quite a lot, we've exceeded that globe model's limit. Remember, the sun's width distance, 965,000 miles and some change. Half sun is 482,000 miles. Again, huge problem. And this shows definitively that the heliocentric globe model does not work. Again, knowing those limits and how we get that and how the breakdown works when we look at the sun size, when we do that actual vertical angle measurement, is breakdown. And what we have to understand is when we're doing that 45-degree sector test, the observer on the globe model is at an angle to the sun already at 45 degrees. So they can only get a 45-degree vertical angle measurement to be within limit. And that's the hard truth, the hard reality of it. Who uses vertical angle in their real-world applications? The two modern-day sciences that mostly use vertical angle in their applications. Why? Lives depend on it. Lives depend on its accuracy and its validity. Within those applications, within those fields of science, military science, especially gunnery, live fire, safety, artillery, small arms, and combat engineers, all use it in the military science, field of military science. And we give you an example of it. Civil engineering, give you an example on a bridge example on it. Bridges, road engineering, building structures, and railroads all use vertical angle. Note, astrophysics is not listed. Why? They avoid it. They avoid using it because it does not work within their model. And again, it exposes the heliocentric as a bad model, a model that just doesn't work. The math just doesn't add up. Military science, how I developed the 45-degree sector box. And again, basically how I developed it, as you can see here, it's just a naked test box. And in artillery, we used these safety boxes. In artillery, we can't see when we're shooting. This is an example of indirect fire. This is the artillery piece firing into an impact area, which has a safety box. You have near, far limit, left, right limit, near, far, left, and right limits in both the impact and the safety box. These are definitive limits. You cannot exceed these limits. If you do, then something really bad is going to happen. You have to stay within those limits. Again, very definitive and very exact science, and that's how I developed this process. It's a very accurate and very definitive process. Again, the naked test box, just a simple geometric box form. Once we fill in the requirements, the information requirements, as this is the 3D version of the 45-degree sector test box. Our OS, we're on sun position 1. We're on manual linear alignment, not vertical alignment, linear alignment. We use a compass and a marks device to get on magnetic north. We get solar noon. And then we have two methods of timing. Time set, if we're using 3-hour time set, we take a vertical angle measurement from the OS to the sun's position, sun position 2 at 3 hours, or we use the sun plot method, if we're going a sun plot or a measured azimuth distance on the globe or flat earth model of 45 degrees. Both of these methods are very accurate. I had a 5-hour conversation with a professor of science, and he admitted, he said, Corey, what you've developed is a very accurate process. He had to admit. And again, these processes are very, very accurate and very definitive. So both methodologies, and remember on the globe model, surface distance equates to surface angle or observer angle to the sun at the time of measurement. So that's one thing we have to include in our calculation for the globe model. And this is how we do it. Measuring distance and surface angle on the globe using latitude and longitude. This globe model has a breakdown of 10 degrees for each square for 36 squares for a 360 degree circumference on these latitude lines. And all we're doing is from our OS position to the sun's 90 degree position. If this was during the summer solstice up in the northern hemisphere, Tropic of Cancer, all we have to do is measure our azimuth to it, the Tropic of Cancer, and then count our degrees. And then in this example, we're 55 degrees or 5.5 squares between that distance between the OS and the sun's 90 degree position to the Tropic of Cancer. Simple addition. 5.5 squares, 10, 20, 30, 40, and 55 degrees. That observer is 55 degrees to the sun before we even start measuring vertical angle. That leaves you only with a vertical angle measurement of 35 degrees to be within the 90 degree limit. Again, the globe model, this geometric form is a huge problem for the globe model. Civil engineering, the other example, vertical angle, we have an example here, bridge height. The underpasses, a semi is 13.6 in height. If we use here and we look at that spread, we remember that spread. This spread is too small for that 13.6 semi to go through. This would be like the right triangle spread. So this bridge height is underpass is only 12'4", so that truck would damage. It would hit the underpass underneath it. It would damage both the tractor and the bridge. Whereas this spread, if we look at this spread, it's a larger spread that would allow for that semi to safely pass underneath the underpass. Again, very simple process, but very accurate. And again, these are right triangles in everyday use in two sciences. The Gleason's Flat Earth Map has a lot of information on it, and some of it's coming out now, but when I first investigated, I did a lot of investigation on the Gleason's Flat Earth Map, and one of the big differences, again, is Antarctica is obvious as the white ring around it. Some people tried to tell me, well, this is actually the globe model squished down. Well, no, that's incorrect, because this is much larger. This area is about 59 to 60,000 miles around the globe. Is only 11 to 12,000 miles the Antarctic continent. So, and these are 1-hour sectors, 15 degrees or 24 for 360 degree coverage. This is a sun position map, by the way. So sun positioning was used to develop this map. On the very top, a lot of people get lost in the sauce for this. The most important part is on the top of the map where you have manual linear alignment on magnetic north, and then the 3-hour timing or 45 degrees left and right. This can be as an excellent tool used to show that how if you're 45 degrees to the sun at 3 hours, that sun has to be 45 degrees in vertical angle. So this is an excellent tool, both easterly and westerly. Excellent tool for teaching how it would work on the actual globe model. Because this outer bend right here, if we use it as representation of the globe's curve, we can do the same thing. Now, how I think the early 47 bird expeditions figured out, if we look at Antarctica here, the white ring hooks in towards the ocean, the big ocean pond or the seas around the flat Earth. Where on the globe model, it's just the opposite. They hook out. And how I think Bird and them figured that out, they're expert navigators, and you have to understand dead reckoning flight, but once they figured out, I'm pretty sure they put transponders along this. You don't need to do circumnavigate the entire flat Earth. You don't need to do it, or the globe. You can do it from a very little area and figure out that the land is hooking in towards the ocean versus land hooking out towards the ocean, out towards the or in towards the inland of Antarctica, which is just the opposite. So if you look at both models, like on the globe model, if we look on the very bottom of Antarctica, we see that it hooks in the land hooks in towards the Antarctic continent, where on the flat Earth model it hooks in towards the ocean. So it's just the opposite. And if you put transponders along a flight path, you'll figure that out real quick. And I think that's what they did. Having a lot of air assets down there, just put transponders along the coastline, mapped it out, and figured, yeah, it's a flat surface, not a globe. So one of the key factors, a lot of information. Illumination, again, tells you how to do distance, latitude, and longitude. So it's got a lot of really, really good information on it. Gleason's 1892 lab. Solar noon manual linear alignment, as I talked about earlier, and that's really the very beginning. You set the geometric edge, that sun survey point, using a Mark's device on magnetic north using a compass. You set that geometric edge, that starting point. Once you do that, it's game on. Then you're measuring sector 1 westerly first, and then the following day sector 8 vertical angle the following day. But you have to set that edge, and that creates accountability within the system. There's no wiggle room or room for error within that. And again, heliocentric science doesn't like that. The sun survey point, what it does in place prior to OS setup, again, setting that geometric edge, what I just talked about, creates accountability within the process and setup. Takes out that wiggle room. In other words, now you're held accountable based on your position, what surface angle you're going to have, whether that model works or doesn't work. Once in place, using vertical angle verifies the globe and FE model's sun position at its said size at its said distance based on the model's surface angle or geometric shape. That is hugely critical. And again, that's a lot of people get kind of lost in that, but this is how we can definitively tell that using vertical angle. Allows for verification of timing based on the survey marker point on Earth for each model's orbital mechanics. We can do that using consecutive day survey points. We can verify not only the magnetic grid, but the grid as well. So that's really important. So a lot of things you can really do with this process, really in depth. Defining that limit, you need to know that limit. Once we define that limit, because the sun is always 90 degrees, again, for the globe model at 45 degrees, the observer is 45 degrees. You can only go 45 degrees. And again, you have to set that edge. And then once you do that, based on which methodology you're using, doing that vertical angle, and some people say, well, that just goes straight up to 45. No, that's incorrect, because once you go over that straight line, go up 46 or 47, all the way up beyond 50, you're in flat Earth zone only. You can only get that on a flat Earth measurement. You cannot, you've exceeded the globe models. You've exceeded over 90 degrees for the globe model. And again, the flat Earth having a huge advantage in vertical angle. And again, what we're physically seeing here, as is shown in this photograph, a line of measure directly center mass of the sun. You have angles above center mass and angles above and angles below and center mass. Really critical what we physically see, what we can physically measure. Real important. Two methods of timing, and this is a slide I had to correct because I had sunplot incorrect, one of the measurements. Time set in testing 45 degrees sector is 3 hours equals 45 degrees. In other words, the sun moves 45 degrees in 3 hours over the flat Earth and the globe model. 3 times 8 equals 24. 8 times 45 being 360 degree orbital check for both models. The best time to use this methodology is during the summer solstice period in the northern hemisphere. The sun has a tighter orbital path. So again, very accurate method. The sun plot, which is a predetermined measured azimuth of direction from the sun survey point at the OS to the sun's 90-degree position in the tropics. Example, if you're doing during the summer solstice up in the northern hemisphere, sector 1, that westerly, you get a grid measured azimuth for 45 degree distance between you and the sun, which would be 260 degrees on a map. We're talking map, which is grid azimuth on a digital map, 260 degree westerly. Then we have to add our 9 degree for our location in North Carolina. We add a 9 degree westerly declination which would equal a 260 degree magnetic. In other words, I orient my orienting station, when I'm going to measure the vertical angle to the sun with, I orient that on 269 degrees magnetic, and I wait for the sun to come center mass, and then take the vertical angle reading and the time of measurement. I think I had 267 on it, which was incorrect. 9 on to 260 is 269. Sector 8 the following morning would be an easterly, again 91 degrees easterly grid. We're talking about grid map azimuth, digital map. We would be 45 degrees from our position to the sun's 90-degree position in the tropics. Then we have to add, to get our magnetic, add a 9-degree negative westerly, which would be equal to 100 degrees easterly magnetic. What we physically orient our orienting station on 100 degrees easterly magnetic, and then wait for that sun to come center mass, take the vertical angle reading and the time of measurement. And that's basically how you do it. It's a very simple process, but we need to understand how to do it correctly. We can check both the magnetic and the grid models using these two methods. And again, this was the second part of the try. I had 2 traps originally within this process. The first original, I didn't include the sun plot because I wanted to invite science to come in. And I knew if I created too good of a process, science wouldn't challenge it. They don't want to come into something they know they're going to fail at. So you have to leave an open door. So I left that open door, open for them to come in, and they did. They eventually came in, and then they found out they got him into science. Professor of science got him into trouble because he couldn't identify the limit, and they're not taught that to be honest, because it gets them into trouble. They don't want to get into vertical angle because they know it's a huge problem. And the second part is we can check the grid. We can check the grid on both models, both the flat Earth model and the globe model. The sun is very, very accurate. And again, military science has been using it for decades to use positioning. I've done it using artillery for positioning and then bumping it against another methodology. Very, very little difference. 99.9% of the time you're going to bump within 1 or 2 mils. Using like grid magnetic, and again, that's how we can tell there's little or no refraction, less than 1/3 of a degree. Very in-depth, accurate methodology. All this can be found in the Sun and Earth Modern User Reference Guide. I was put out in October of 2023. There's a 16-step 16 task checklist. It breaks down if you've never used a compass. I teach you how to do that. There's a 9-step geometric validation process is broken down. There's test data from Operation Resolute Time and Operation North American Sun. All that is within the book, and it's available on Zilibris Books or also on Amazon Books. Also, Walmart and Everland there's a couple other places as well that it's coming. It's becoming more and more popular, going out to different places. And again, a lot more people doing testing of their surface shape. Russia was one of the first ones. They did 2 tests. One receiving 45 degrees at one direction and 50 the other, which failed in Russia. So they were one of the first to perform the 45-degree sector test, and it failed in Russia. So lots of other folks doing the testing as well. And again, this is all available in Sun and Earth Modern User Reference Guide. Really a great book. This concludes this week's presentation 11.1, Part 2, putting it all together using the sun, the redo of Part 2. I'm Corey Kell, creator of FlatEarthIntel.com. Thanks for watching.